Yeah, thanks for the opportunity to speak here. So I'm just going to tell you about a paper that I wrote a while ago with Raphael Busso, Pratik Rath, and Arvind Chabadli-Moganam. And the talk is basically going to be about a combination of things. Part of it will be about studying certain aspects of modular flow in quantum field theory. And then part of it will be about the area operator in classical gravity and how they come together in the context of ADS-CFT. And probably I don't need to provide too much motivation for these individual things for this audience, but let me just say a few words about why, for example, modular flow is something that's really important to think about properly in quantum field theory. So, should probably write bigger. Also, my handwriting is comically bad, so if you can't read anything, just let me know, and I'll try to write more clearly. So, modular flow has led to a lot of really important results in quantum field theory over the last few years. I'm just going to name two of them that are particularly important. The first of them is a proof of the average null energy condition, which was due to Faulkner and collaborators from a while ago. And the other one was a proof of the quantum null energy condition, also due to Faulkner and collaborators. Both proofs made heavy use of various properties of modular flow related to causality and analyticity of correlation functions. They're pretty abstract, but they result in statements that are extremely universal and rather profound properties of quantum field theory. Basically, energy conditions, both global and local. And in the context of ADS-CFT, modular flow is pretty ubiquitous. It was used, for example, to prove entanglement wedge reconstruction. Faulkner's name is going to show up a lot in this talk, just as FYI, because he does a lot of modular flow stuff. So entanglement wedge reconstruction was something that Faulkner and Aitor Lefkowitz worked out using modular flow. And actually, even more generally, bulk emergence, the concept of how space-time geometry emerges from properties of information theory on the boundary is something which you can make very explicit using the concept of modular flow. You know, with those kind of basic motivations aside, I'm just gonna start by giving you a very broad strokes overview of the aspects of modular flow that are going to be relevant for this talk. So the first thing I'm going to do is assume I have some quantum field theory in which the Hilbert space factorizes into two parts. And typically, this factorization is going to involve taking some Cauchy slice in the quantum field theory, splitting the Cauchy slice into two parts, A prime and A, and then decomposing the full Hilbert space into a Hilbert space for A prime and a Hilbert space for A. In this kind of setting, where you assume there's a factorized Hilbert space, you can define what's called the one-sided or half-sided modular Hamiltonian, which is defined as follows. So basically, you just compute the reduced density matrix of A prime in some arbitrary state psi, and then you take the log, and this is called the half-sided or one-sided modular Hamiltonian associated to A prime. And once you have this object, you can define what's called a half-sided modular flow, just simply defined as follows. You don't really need to specifically define this, but it's essentially the generator for this flow. And it generates what's called a one-sided module.
What sort of operator is this? This flow?
What sort of flow is it? Yeah, I'll get to that. In general, it's just some very complicated non-local transformation of the state that doesn't have a very simple geometric description.
Is it like an isometry or something?
Yeah, so in general, it's not. And I'll describe this in the particular case where psi is the vacuum state. And this has a connection to like the boost isometry in quantum field theory.
You're only boosting half of the.
Yeah, this is just on one side, just for 8 prime. All right. Okay, so this is just so far, there's just some quantum field theory statement. And it's still as part of the motivation, there's a famous result due to the authors Jafferitz, Lefkowitz, Maldacena, and Su, which I'll just refer to as JLMS, which is a statement about ADS-CFT. And it basically says that if you specifically consider the setting of some boundary CFT that's dual to some ADS bulk, then this half-sided modular Hamiltonian is actually equal to the area operator of the Ryu-Takayanagi surface. Plus there's some tiny corrections that don't matter right now. So A hat over here is just the area functional associated to some Ryu-Takayanagi surface that's anchored to this boundary region A prime. And so the claim is that for any state, whatever the bulk dual is, the area operator generates the bulk dual of this half-sided modular flow. So this is an extremely important result in our understanding of bulk emergence. And not only does it allow for a deeper understanding of how geometry arises from some information theoretic aspects of quantum field theory, it also allows you to understand properties of modular flow from just by studying aspects of the area operator. And it's a bit stronger than simply saying, the area is related to the entanglement entropy, because this is an actual generator that, can act on states, it can generate new states. It tells you a bit more. So I want to dig a little bit deeper into this one-sided modular flow.
What does the area operator act on?
The area operator acts on the bulk geometry. This is also something I'll talk about more carefully later, but for now it's basically just you know what, I'll describe it more carefully.
So how does the psi appear on the right hand side?
So the psi on the left is dual to some particular geometry in the bulk, and perhaps some state of bulk fields. The state of the bulk field shows up in that order G Newton to the 0 that I've not talked about, but at leading order it determines what the actual bulk geometry is.
Yeah, but I guess there are also some states where you can't say anything that you don't know. Like some generic state will not have some.
Yeah, it has to be a holographic state. Yeah, that's right. Okay. So I made a big deal about this one-sided modular flow, but it's actually not a very nice object to talk about in quantum field theory. And that's basically because this object here, which I'll write down again, it leads to infinite energy in this state. And the basic reason for this is this one-sided modular flow, very, very close to, like, let's say I take a standard setup with a Rindler horizon. Here's the like Rindler bifurcation surface. There are general results where you can roughly show that when you just focus on what this flow is doing to the state, very close to the Rindler horizon, it essentially acts like a boost, an ordinary Rindler like boost, but just on one side. So this object very close to the Rindler horizon will look like a one-sided boost. It only acts on this side, so it doesn't do anything on this side. And it does this for a generic state. When what that means is in quantum field theory, we have something called a universal type 3 vacuum entanglement. All that means is modes over here are going to be entangled with modes over here in a very, very specific way so that the vacuum is smooth, there's no energy anywhere. But if you do a one-sided boost, then you're going to change the phases of the modes on one side without changing the phases of anything on the other side. So you're actually going to leave the very fine-tuned state that corresponds to a smooth vacuum. And the effect of that is you basically end up getting a state where there's an infinite amount of energy basically propagating along the Rindler horizon. So it's not a smooth state. It's not a very good thing to do. Usually we ignore these things, but for the particular things I'm talking about, this is actually going to be important. So one of the questions that we want to ask or study is there a version of this half-sided modular flow that generates a smooth state? There's no weird infinite energies, things like that. The other half of the question is this object over here, the area operator, as you asked like, what does it actually do? It's a very formal object. And we often just talk about it in a very simple way in the context of classical gravity as just the area functional of a surface. But this question, which will end up being related to this question of whether this half-sided modular flow is smooth, is something I want to ask. So what is the action of the area operator, at a very precise level? So, and lastly, I'm going to ask how are 1 and 2 actually related to each other? So that's the basic motivation for what I'm going to talk about. Are there any questions so far?
So when you say smooth, you mean that something like the operator remains bounded at varying s or something like that?
Basically, the state doesn't have any infinite energy in it. The energy of it's allowed to have energy densities that don't behave well, but if you integrate the energy across the Rindler horizon, it should be finite.
So the energy, if I take any sort of open set and I integrate the energy there, I should always get something fine.
Yeah, after doing some analog of this one-sided modular flow. Okay.
If I start from any such state.
That's right. But I should say, and I'll make this clearer later, I'm specifically going to be talking about this kind of setting where I have a Rindler horizon and I'm basically the A will be the half space on this side and A prime will be the half space on this side. You could consider more complicated regions like spheres and things like that, but they get very complicated and it's much harder to analyze what actually happens. Okay. So I'm going to first talk about the modular flow part, then I'll talk about the area operator part and then how they're related. So in order to talk about the modular flow part, I have to tell you a little bit about what the basic aspects of Tomita-Takasaki theory. Essentially, due to Tomita, Takasaki, Borchers, it's a set of results that formalizes properties of modular operators and modular flow. We don't need too much of the complicated details. I'm just going to give you a few basic definitions and work up to the relevant objects, which will formalize this modular flow here. So the first thing that you usually define is something called the relative Tomita operator, which is usually written as S. So the relative Tomita operator requires two inputs: the state psi you're interested in, and then the vacuum state. And it's defined as an operator which has the following property. So if you give me some region A, could be this region A, for example, it could be A prime, whatever region A, there's an algebra of operators associated to that region A. And the Tomita operator is the operator which, when it acts on any operator in this algebra, maps it to the acting on the state psi and maps it to the conjugate acting on the vacuum. It's just a definition. You can always find such an operator. It's a non-trivial statement, but yeah. Once you have the Tomita operator, you can define the object that we will mainly care about.
This is not a linear operator, right? It's like an antilinear.
But you can't what, sorry?
Is that like an antilinear operator?
This is not antilinear.
It is actually.
Oh yeah, delta. Sorry, yeah, it's antilinear. Sorry, yeah.
The algebra of operators is the algebra of any operators, really?
Algebra of what, sorry?
The algebra of operators in which
act on A.
So yeah, is it any operators now or?
Bounded, like bounded. I mean, they should be nice operators. They shouldn't. Is that your question? Like that? Are they allowed to?
Not self-adjoint in particular, I guess.
No. I don't think it has to have specific restrictions like that. As long as they're like bounded linear operators.
But there aren't many bounded linear operators usually.
Huh?
Most interesting operators tend to be unbounded in life. Except you.
I don't. Yeah.
Usually you consider spectral projection.
Okay.
Yeah. And yeah, thanks for correcting me. This is antilinear. Right. So the thing that we'll mainly care about, which you define using this Tomita operator, is called the relative modular operator, and it's simply S staggered times S. That's the definition of it. Okay. There's another way to write this in terms of a sort of a polar decomposition using a modular conjugation operator, but that won't actually be relevant for this talk, so I won't talk about it for now. This is really the only definition that is important. Okay. Oh, actually, I can just define what I need to define here. Okay. Now, once we have this relative modular operator, I'm going to define an object called the cocycle flow. Okay. So the cocycle flow is simply defined as follows. I'll write it down first, and then I'll try to provide some intuition for it. So it's equal to, and I apologize, there's a bit of notation that I'll just quickly unpack. Hope you can see this.
It actually is a little more.
Okay, so I'll rewrite it again. Okay, I'll just rewrite it. So, I just abbreviated as CC flow, cocycle flow. Define
Follows.
Oh, sorry. Okay. The prime over here just means it's the modular operator associated to the complement algebra. So we started with the modular operator defined for the algebra of A, and the prime just means it's the modular operator associated to A prime. So it's just a convention to pick one side and then define with respect to the other side. It's just a convention thing. Delta of omega is the modular operator specifically for the vacuum state. So here I talked about the relative modular operator, but you can also just define a modular operator for the vacuum itself.
Where you take psi to be the same as momentum.
Exactly. Yeah. Okay. So right now this is just some formal definition. What I'm going to do now is assume that I can write all of these things in terms of density matrices, just to provide a bit of intuition for what this object is, because it just looks like some crazy thing right now. Normally, you're not allowed to do this because we're dealing with type 3 quantum field theory, and writing down density matrices assumes you can use a factorized Hilbert space. Everything I'm about to say you can prove without using density matrices, but it's just overly technical.
So I think what you wrote up there for cocycle and what you wrote down there,
Yeah, sorry, this should be flipped.
The convention you're using is, yeah.
I'm using Faulkner's convention, which is very different from what I think the community normally uses, but it's just what I'm used to at this point. Yeah, apologies.
Why is it called cocycle?
It satisfies an identity which has something to do with like cocycles and groups, but I mean, Nima might understand that a lot better than I do. It's a very mathy. I don't fully understand. Yeah. Some group theoretic property that it satisfies. Okay. So in terms of density matrices, you can write down what this modular operator is, this relative modular operator. And it takes the following form, using the same notation from earlier. So the relative modular operator is rho psi of A prime inverse tensor rho omega of A. So now what we can do is just take this definition or this relation and plug it into this and see what this cocycle flow is basically doing. So if you do that, I mean, it's just a few simple steps. You can check that the cocycle flow reduces to the following statement. Okay.
How do we go from delta to delta prime?
Yeah. Yeah, it's not at all obvious. Again, there's a bunch of results you can derive for the relationship between delta and delta prime. But basically delta prime to the IS acting on psi is equal to delta minus psi.
Here we're assuming
Plus,
that
it's either plus or minus, I can't remember exactly.
here we're assuming that the union of the algebra A and A prime is the full
It's the full algebra, yes, because I'm assuming that the slices we're talking about are Cauchy slices. Yeah, exactly. It's either a plus or a minus. I can't exactly remember. And I always get confused by whether it's a plus or a minus, but they're basically a relationship that just takes one to the other. It's probably a plus because I think delta times delta prime is the identity.
It's not true. It's not true that it's being assumed they're no plus or minus. Even if they're contained in A tensor A prime.
Yeah. Okay, so this is the thing I was talking about earlier when I talked about with the minus, but yeah, half-sided modular flow. And this is the thing which I said produces infinite energy in the when you apply it to a state. So what's going on here is we're first doing half-sided modular flow with respect to psi, and then we're basically undoing the vacuum part of that half-sided modular flow. So remember how I said very close to the Rindler horizon, this object will basically act like a boost. You can make that statement more precise, but the infinite energy is basically coming from messing up the very, very high energy modes that are entangled basically the same way that they're entangled in the vacuum. So what the CC flow is doing is just undoing the vacuum flow and making sure that you only flow the excited modes. And that's the rough reason why it leads to a smooth state. It doesn't produce infinite energy. It's just fixing up whatever you messed up in the vacuum. The more precise statement is that this thing has a finite average null energy. Which you can just calculate and check, but it's a very technical calculation to check this. And I'm not sure it's particularly any more insightful than the statement that I just said. Another important point is that
It's finite when you integrate, or it's
Yes.
finite point-wise?
It's not finite point-wise. It has it can. I'll talk about that in a second. It can have delta function, but yeah, it's finite when you integrate. The other important thing is that this object here, the CC flow, is actually in the algebra of A prime in this case, which is a non-trivial statement. This object, for example, doesn't belong to one algebra or the other. It doesn't belong to the algebra of A or A prime, but this object does belong to the algebra. So it's an operator in this algebra, which, as far as I know, Edward or Nima, you might have a better way of thinking about this. It's a pretty non-trivial result that requires, from what I can tell, a rather technical proof. I don't know of a very intuitive way of convincing myself that this ought to be the case, other than the fact that it produces a smooth state and it doesn't mess with the entanglement between the near horizon modes. But it's not very convincing.
If there's a simple argument, it would be that it commutes with A, and therefore is contained in A prime.
But it could be unbalanced. So
Yeah.
it's in the commutant, but it's not necessarily the algebra. There is an argument of Cohn, which, it's not too complicated, but it's not necessary.
But it's manifestly bounded because it's unity.
Well, based on
Before going to density matrices, it was manifestly unitary.
Yeah.
It's true. And then if you show that it commutes with A,
it's a partial isometry. It's not really unitary. It's unitary if it's there are each leader states.
Like cyclic and separating.
Yeah, cyclic and separating.
Yeah.
These are
Well, let's
technicalities.
assume, if they're cyclic and separating, then I guess it does follow pretty directly. Yeah, otherwise it can be complicated. Yeah, I'm going to assume they're cyclic and separating because I don't think any of the fundamental insights really depend on that. Okay. I'm doing this. I'm going to write down now what's probably the most important property of this cocycle flow. So let's say I take an operator O prime, which is in the algebra of A prime, and I ask, what is the expectation value of O prime in the cocycle flow state psi s? Again, you can prove this very formally, but I'm just going to use density matrices to make it as intuitive as possible. So if you write out what the cocycle flow is in terms of the density matrix definition that I wrote over there, which you can't see here, whatever. If you write it out, it ends up being the following thing. And just to emphasize, I haven't done anything here other than just plug in the definition that I showed you earlier. I'm just writing it out in terms of a trace. All I've done here is plug in the CC flow, and here's O prime. If you use cyclicity of trace, and just bring that last factor over to this side, you can push it past this row psi, and those factors cancel out, and you'll just end up with the following. In other words, if you take any observable in A prime and compute its expectation value in the CC float state, it looks the exact same as if you just did the vacuum modular flow of that operator. So let me write that out more. Please. Sorry. Okay. So this is only true for observables that are in the algebra of A prime. If you take an observable in A, then nothing is going to happen to it, right? Because as I said earlier, the CC flow is in the algebra of A prime. So it commutes with anything that's in A, so it's not going to transform observables that are in A. So observables in A don't transform at all. And observables which stretch between the left and the right, basically, you want to compute, for example, a 2-point function of O prime and O, that doesn't have any simple description. But like that's just some complicated mess. But these left-sided observables are simply given by vacuum modular flow. And why is that important? So the reason that's important is a very famous result due to Bisignano and Wickman, that the vacuum modular flow is just a boost generator. In other words, the vacuum modular flow is just the operator which generates this transformation. It just does a global boost of Minkowski spacetime. Specifically when you're considering this sort of half space situation, this Rindler horizon situation that I just talked about. So what that means for this statement over here is, for example, let's say we have a situation where I take some slice here, and let's say I have, here's just the time evolution of some particle that's just sitting around over here. Here's some particle that's sitting around over here. And I apply the CC flow. And what the CC flow does is it does this boost only on the left side, because it doesn't do anything to observables on the right, and it just acts like vacuum modular flow on the left. So in the end, after applying CC flow, you'll get something like this. Easier to see.
I'm not supposed to trust for this in the future.
You're not supposed to, exactly. Well, the fact that it acts like a boost is only true specifically in the left wedge. You don't know what it does here or here. But you know, the picture I'm drawing here is more just suggestive of the fact that because you boosted something here and didn't boost something there, they'll if they didn't collide before, they can collide in the future. But if you have an observable here, then yeah, there's no simple description. Yeah.
So you're considering applying the cocycle flow to the state with two excitations in ANA prime. Is that what you're considering?
Or just as an example, yeah.
It will not be the boost of left and not doing anything to right. It will be something complicated. If you don't have anything on the right, it will be boost of left.
Yeah, sorry, I'm not considering some kind of 2-point function between these two excitations. I just mean separately, it won't do anything here if you just consider an excitation there, and here it'll just boost it. Yeah. But yeah, future and past observables don't have any simple description. Okay. So these are all just expectation values that I've talked about so far. I just want to mention one last thing, which is what happens to the entropy in these cocycle flow states. So the relative entropy in terms of this Tomita-Takasaki language is defined in the following way. And I'll just quickly draw a picture to explain this notation real quick. But it's just the expectation value of the log of the modular operator in the state psi that you care about. And V here, the specific setting in which I'm considering, V corresponds to the following. Okay, so this is the Rindler horizon. This is the null plane. This is the V direction. I'm considering some cross section or some cut of the Rindler horizon that has some arbitrary profile. Instead of a flat cut, the Rindler horizon, you can just imagine some crazy wiggly slice of along the Rindler horizon with some profile V of Y. And this is the half space that I was drawing earlier. And I'm computing the relative entropy of psi with respect to omega for the observables that are associated to this complicated cut B of Y. And that's defined as follows. Okay. Any questions on that picture or the definition there? All right. The only relevant fact about relative entropy here is that the CC flow satisfies a sum rule when evaluated in this kind of setting. And the sum rule is basically the following. So P here is the average null energy operator. P sub S just means the average null energy operator evaluated in the cocycle flowed state, whereas P naught is just the average null energy operator evaluated in the original state without the cocycle flow. So this sum rule basically relates the average null energies in these respective states to a shape derivative of the relative entropy. So here I'm taking the relative entropy defined on this cut V, and I'm taking a functional derivative of it with respect to V, and then I'm evaluating it on the flat cut, this thing here, which I've just called partial A. This is a highly non-trivial sum rule, and it basically follows from various analyticity properties of these cocycle float correlation functions. And it's derived in this paper by Faulkner, Shehan. I'm going to use it in a second to give you some intuition for what's actually going on when we talk about not just one-sided observables in the CC float state.
Zero is the expectation value of the stress tensor in the vacuum, or
In the non-cocycle float state. So like when S is 0.
S equal to 0. Fine.
Yeah, sorry. Yeah. Okay, so with that sum rule in mind, what I'm going to do now is use a very standard decomposition of the relative entropy. So the relative entropy is just equal to the expectation value of the modular Hamiltonian minus the entanglement entropy, all on the state side, where the modular Hamiltonian here is the modular Hamiltonian of the vacuum. And this is the same Bisignano-Wickman theorem that I described earlier. It has a very simple form. Its particular form here, it's not too important for you to know the exact factors and everything here, but all I'm writing down is the boost generator. So the modular Hamiltonian is just some integral of the stress tensor with this boost weight.
Lots of V's in the formula.
Yeah, so let me explain what the V's are. The Y here corresponds to the transverse directions of the Rindler horizon. So if the Rindler horizon is d-dimensional, Y is the d-2 spatial directions, basically. The little v is the null direction along the Rindler horizon.
Sorry, which one is the
Little v is this one. Okay. Yeah. And then big V is a particular slice of the Rindler horizon. It's just some arbitrary profile that corresponds to some cut, like, yeah. Does that make sense? This difference here is just the statement that I'm doing a boost about the cut V of Y. So it's a fixed point of the cut V of Y and then boosts everything else. And this is just the expectation value of the stress tensor, the VV component of the stress tensor in the state side. Little v. Okay. So what I'm going to do is just decompose this average null energy operator in the state side, in the cocycle float state into two parts. And I'll explain what these two parts are. Okay, so what have I done here? I've basically broken up the Cauchy slice into two pieces and introduced a tiny little epsilon ball around partial A over there. And I've applied the CC flow. So what it did is it boosted everything. It boosted the left part. This is just an observable like associated to the left algebra, right? Because I've introduced this little epsilon ball. So I boosted everything on the left, and I haven't done anything to the part on the right. Okay. Now what you do, I won't go through the details, but now what you do is you take this form for PS that I just wrote here, plug it into that sum rule, and then decompose SREL in this way here. Plug that into the sum rule. And if you just work out what happens in the limit that epsilon goes to 0, you find that there is a shock in the stress tensor in the CC float state. That last thing there is a delta function, which only fires when you're at this this surface, this codimension 2 surface, partial A. So basically, you should think of this as like a gluing condition, similar to the gluing conditions in general relativity. So we started with 2 wedges, the left and the right Rindler wedges. You can imagine breaking them up, boosting the left wedge, doing nothing to the right wedge, and then asking, what do I need in order to glue the 2 wedges back together and get a consistent state in quantum field theory? And the answer to that question is you can glue them back together as long as you have this stress tensor shock that's localized to the codimension 2 surface when you're gluing them together. And that shock is entirely fixed by the shape derivative of the entanglement entropy at the gluing point. All right, so what's that?
That's right there.
Oh yeah, they told me not to write there, but I guess, okay, got it. Okay, just one last thing, and then like most of the talk is pretty much done, and then I'll just talk about gravity after that. The last thing I'm going to do is just describe a simpler way to think about the CC flow in terms of what we call the precursor slice. And it's really simple. So I'm just going to draw a picture for it. I don't think the equations are too relevant. Here's the slice A that we started with. Instead of talking about the CC flow on this original slice, let's just talk about the state on this boosted slice. I'm just going to call this slice A prime of S. So in terms of equations, all I mean is define a state psi s on A prime of S, I guess union A, but point, which is just half-sided modular flow of psi on the original state. So basically, all the precursor slices is you take psi on A prime and just do a half-sided modular flow with respect to A prime, but then you put the state on this kink slice here. And if you want the CC flow, you can just evolve back to this using the boost operator. I'm distinguishing this from the state you get by just doing half-sided modular flow on this original slice. If you do that, you get the infinite energy I talked about earlier. So what I'm saying here is do half-sided modular flow, but then put the state on this kink slice, and that acts as a precursor to the CC float state. This is smooth because the kinking of the slice cancels out the infinite energy that you get by doing the half-sided modular flow. All I've done is absorb the vacuum modular flow and CC flow into a change of the slice on this side. And the only reason I've done this is it now makes it very easy to understand what the analogous thing in gravity should be. Okay, so this is all quantum field theory so far, but I want to understand, is there something analogous to this object when we talk about general relativity? And this picture will make it very very clear what that picture, what that construction is. And the object I'm going to call a kink transform. Because motivated by this, it's going to basically be kinking a bunch of slices. So recall that in general relativity, if I want to specify a solution, I can just specify initial data on some space-like Cauchy slice, and then just that generates whatever the solution is. And the initial data corresponds to an induced metric and an extrinsic curvature on some Cauchy slice sigma in my space-time, right? So now I'm going to define a transformation where I keep HAB fixed. So HAB is the induced 3 metric or whatever, D-1 metric on the slice. I'm going to keep HAB fixed and I'm going to change KAB. And I'm going to change KAB in the following way. And let me just draw a picture for this. So here's some slice sigma. Here's some codimension 2 surface R. Could be any codimension 2 surface so far. And all I'm doing is I'm going to take the extrinsic curvature on this slice, and I'm going to shift it by a delta function, which is supported purely on this codimension 2 slice R, where this X here is just the unit. So there's a time-like unit normal T, and there's a space-like unit normal X. Right? So X is a space-like unit normal to R. That's within the slice sigma. So essentially, all this picture is doing is taking initial data in GR that looks like this, and converting it to initial data that looks like this. Like that's the picture that you end up getting. Okay. So what I'm trying to do here is formalize what a half-sided boost is in gravity. In quantum field theory, you can just do a half-sided boost pretty much across any surface, and this stress tensor shock guarantees that it's well-defined. In gravity, you would imagine you could just do this across any surface, but when you change the extrinsic curvature in this way, you have to make sure that you still satisfy the constraint equations of general relativity. You're not just allowed to do this for free. I think I'm just going to use it here. I don't feel like it. So the constraint equations of general relativity break up into a Hamiltonian constraint and a momentum constraint. And I'm not, again, the details aren't too important. The Hamiltonian constraint basically just says the Ricci scalar plus the trace of the extrinsic curvature squared plus k squared is equal to the stress tensor in the time direction. And the momentum constraint is just some statement about derivatives of the extrinsic curvature. So it's a simple exercise. Basically, take this thing I've defined here, this kink transform with this delta function in the extrinsic curvature, plug it into this constraint equations and see when it's satisfied. And as it turns out, it's only satisfied if R is an extremal surface. And I'll talk about the implications of this a bit more, but to at least to me, that was really surprising, because what I'm defining here is basically a half-sided boost. It's just some geometric action in gravity. You would think you could just do that across any surface. Like why does the nature of the surface matter? But if you define it in this particular way in terms of the initial data, it only ends up working across extremal surfaces. So the punchline is that this kink transform requires R to be extreme. Any questions so far? Okay. Another way you can think about this, just really quickly, is similar to the quantum field theory setup. Take the domain of dependence associated to this side of your Cauchy slice and take the domain of dependence associated to this side. Break it up into two parts and glue them back together with a different relative boost angle between the two sides. So essentially, what you're doing is generating new solutions in gravity simply by changing the relative boost angle at which two slices are glued back together, which is analogous to what you're doing in quantum field theory. That's the sense in which this is sort of like a gravitational version of a one-sided.
I'm just a little bit confused. Is it okay that there is a distribution appearing in the curvature?
Yeah, you might worry that because it's distributional, like solution for distributional source for Einstein's equations, maybe causes some problem. At least if you analyze what's happening in a neighborhood of R, this co-dimension 2 surface, everything looks okay. It's hard to say what happens in the future of the past wedges. You know, if you actually time evolve it very far into the future and the past. But for example, one specific case you can consider is a two-sided black hole. Do this transformation, and you can convince yourself that like it's perfectly smooth. So basically, when R is a compact surface. More generally, I expected that it doesn't have any problems. I think, yeah.
The solution might be non-smooth. Possible exists in general, but isn't always generic and non-smooth.
Yeah, what kind of, do you know, like, do you have an intuition for what kind of non-smoothness is supposed to show up? Like, it's an integrable.
I'm not sure what happens, but I'm sure all kinds of non-smoothness can propagate over an all plane. So I think it might happen.
Yeah, okay, yeah, you do, there are gravitational shocks that'll show up, like delta function.
That's all I meant by non-smooth.
Yeah, that's right, yeah. Okay. Okay, so that's really the crux of most of it, because now all I was going to do is convince you without too much effort. Do you know how much time I have?
Yeah, maybe 10 more minutes.
Okay, yeah, I don't need that. I don't. There aren't too many details left. So now you just take this kink transform and apply it to ADS-CFT. I've already done most of the work in setting it up in a way that it's probably immediately obvious to you that if you do this kink transform in ADS-CFT, its boundary dual is going to be the Kahn's cocycle flow. So I don't even need to write too much there. What I'm imagining now is you take R to be the Ryu-Takayanagi surface on some ADS spacetime that's anchored to some boundary region. The boundary region will take to be some bifurcation surface that corresponds to a Rindler horizon. And if you do this kink transform, it's going to kink the slice in the bulk. And it's pretty easy to check that this kink slice corresponds to, on the boundary, it intersects the precursor slice that I've defined over there. So observables in the left in the bulk will get mapped to the precursor slice observables on the boundary. So all the one-sided observables very trivially will match between the bulk and the boundary. Basically, because you're not doing anything to the domain of dependence here other than boosting it, and you're literally doing nothing here. And that's exactly what the CC flow does. So the non-trivial part of matching the bulk and the boundary is the fact that there is a stress tensor shock in the CC flow at the entangling surface. How does the kink transform reproduce that? Or is there some analogous thing in the bulk? Again, I won't really go through the details. But the main point is just that there's the shock here in the extrinsic curvature. right? Just evaluate that shock near the boundary of ADS. One way to do that is to just use Pfefferman Graham coordinates, just write down some expansion of the metric near the ADS boundary, work out what the shock is in those coordinates, and you can check that it exactly reproduces the stress tensor shock on the boundary, where the entropy basically comes from the position of the RT surface. Not too important, but the main thing is just that there's a very clear match between this kink transform gravitational shock and the stress tensor shock in CC flow. So the upshot with all the words that I said is that kink transform in the bulk corresponds to the CC flow on the ground. Now, the title of what I said was the area operator in gravity and holography. And I haven't actually said the word area operator since the very start. But my claim, which hopefully is not too surprising, is that this kink transform that I've defined is just the area operator in classical gravity. And the reason for that is there's this famous result by Wald from many, many years ago, which says that if you give me some, actually Anima had a paper from a while ago that's related to this. If you give me some codimension 2 surface in gravity, you can always find a boost vector field in the neighborhood of that codimension 2 surface, which acts like a one-sided boost. And if you calculate the Noether charge associated to that, it's just the area. So, here's some codimension 2 surface in gravity. In the immediate neighborhood of it, there's always a vector field C, which acts like a one-sided boost, and the Noether charge Q associated to C is just the area of R. So there's a formal sense in which the area operator is the one-sided boost, but like when people like Wald talk about it, it's just some statement about Noether's theorem. Here, the kink transform is literally what the area operator is doing in a very explicit and rigorously defined sense. What's non-trivial is that its action only makes sense for extremal surfaces. When people like Wald or relativists talk about the area operator, it's just something you define for any surface, and you just assume, yeah.
Well, I didn't mean to go finish your sentence.
Yeah, I was just going to say, from the perspective that it's usually talked about, at least to me, it's a bit non-trivial to see why extremal surfaces would be special. You'd have to work out the Poisson bracket of how it acts on geometric data and things like that. From this perspective, I think it's a lot clearer that extremal surfaces end up being special for the area operator. Yeah.
I think Wald might have said the following. To define a flow on phase space, he would use Poisson brackets of some gauge invariant function on phase space. Now, the area of an extremal surface is a gauge invariant function. But unless you have some intrinsic way to describe a particular surface, you don't get a gauge invariant function on phase space.
Yeah.
If you had some other way to describe a distinguished surface, the area operator would be some well-defined thing, maybe interesting, maybe not.
Yeah, so but for example, another example of a gauge invariant surface would be, I think, you could just say, you could define a surface that satisfies this, for example, right? Or
that will not be well behaved. You could think of something. You should add K to it or something. So why is there an area surface? It's important that the equation of extremality is elliptic. So that if you change the space-time a little bit, there's a nearby solution.
Okay.
If you are too crude in what you write down, that won't be true. Okay. You won't really get a well-defined surface. But your general idea was correct. Instead of saying that K is 0, you could. There are things you could have said that might have made sense.
Yeah.
If one's too careless, one will write something that doesn't make sense.
Right.
Your general idea makes some sense.
Yeah.
And I'm not sure it's wrong.
Yeah. So I guess basically you can imagine there are other gauge invariantly defined surfaces, but somehow the area operator seems to really care that it's extremal.
Like causal holographic surfaces.
Yeah, like a marginally trapped surface. for
Marginal
example.
trap surface.
Yeah, from a PDE point of view, I don't know how well defined they are, but at least in GR, it's supposed to be a meaningful object to consider.
Marginally trapped surface is defined in a given hypersurface.
Yeah, exactly.
So here you want something which is defined, and then you have the problem of saying which hypersurface you want. You need to have something which is defined in space time with no additional information.
Yeah, that's fair.
So, but I would question that there might be something that would work. And then you would get a function generalizing the area function. And it would make at least some sense to consider whatever generates from Poisson brackets.
Right.
You might get something which was too singular to be very meaningful.
Yeah,
Here you got a relatively mild shock.
that's right. That's right. That's right. Yeah. Okay. So, okay, I'm gonna pretty much wrap up. Don't have much more to say. There's two more things I wanted to say really quickly. The first thing is I started off by talking about JLMS, and this is very similar to JLMS in that it's a relationship between modular operators and area. I think the difference between these is summarized by this picture that I'll just draw quickly. This is ADS. I'm going to split the space into two parts, the boundary into A naught and A naught prime. And here's where the entangling surface is. Here's some are. The half-sided modular flow of JLMS is not smooth, as I said, generates infinite energy shocks. And unless you're in the two-sided black hole setting, you're in like a normal case where the RT surface anchors to the boundary, the shock will propagate into the bulk, and the future and past are not going to be smooth. But the area operator isn't supposed to generate infinite energy shocks in the future and past. The way that the equality, JLMS equality, I think, should be understood is when you do half-sided modular flow, you introduce a little bit of a regulator on the boundary between the left and the right half spaces. In the limit that this regulator goes to 0, then you're going to get something singular. But then the bulk picture of this is you're going to have tiny brains that stick out. And the JLMS equality works in this setting where you have these slightly modified boundary conditions for ADS. So basically, half-sided modular flow on a given slice is dual to the area operator if you have these modified boundary conditions. Or what I think is somewhat easier is if you use the CC flow instead, then all you have to say is the area operator in the bulk is dual to the half-sided modular flow on the precursor slice on the boundary, and then you don't have to modify the ADS boundary condition by introducing these tiny little brains that stick out from the regulator. So that was my first point. And my second point is you could ask what happens to this whole story I've just described if you include quantum corrections in the bulk. And it's actually pretty nice what ends up happening. So when you include quantum corrections, as we all know, you should really talk about the quantum extremal surface instead of the Ryu-Takayanagi surface. And the quantum extremal surface has the property that the expansion, for example, in the time direction, is the derivative of the entropy in the time direction, just being a little rough here. And the expansion in the space direction is the derivative of the entropy in the x direction. If you take these relations for the expansions and plug it into the constraint equations for general relativity that I wrote earlier, so instead of assuming it's extremal, assume it's quantum extremal, then you actually recover exactly these shocks, but now in the bulk. So it seems really suggestive that there's some sort of notion of a CC flow, a cocycle flow that's happening in the bulk of gravity as well. That in order for it to be consistent with the Einstein equations when you have quantum fields propagating around. Now I say suggestive because actually making sense of a CC flow in gravity when you're also doing the area operator is really difficult because the area operator is changing the geometry and you also want to ask what happens to quantum fields as you're changing the geometry. And comparing quantum states on two different backgrounds is pretty complicated. So it's not immediately obvious to me how to formulate that very well, but to me, it seems really suggestive that you get the exact same kind of shock, but now in the bulk space-time. So I think if there are two lessons here, the first is that this is some sort of Lorentzian example where the area of the extremal surface seems to be really special for the area operator, and there's some generalization of the algebraic QFT framework to curved spacetimes where CC flow, I think, would fit very naturally with how the area operator works in gravity. Yeah, and I'll stop there.
More questions for when? Right, if not, let's thank Ben again.